Alright, so the short talk will be the story about the PGMLab and its use for biomarker discovery. Do you hear me on the back? Not so? That's my voice. We don't have a microphone, I'm sorry. Okay, so PGMLab was developed by our machine learning specialist in Stein Lab, Hossein Al-Atfal. And what it does, it integrates the network knowledge, for instance, gene network or a pathway with any omics data like DNA mutation, gene expression, copy number variation, protein data. And it gives as output two types of models, a generative one, for instance, subtyping patients, and a discriminative model, for instance, drug sensitivity prediction. So it started on late last year, and the plan was to use curated pathways from Reactome here, and any type of omics data we have in our hands, run through PGMLab, take the outputs of posterior probabilities for all the nodes in the pathway. We select specific key outputs that shows that the pathway is either on and off. We add clinical information and eventually do biomarker discovery. So we used, for the beginning, copy number variation for a team cohort of 344 samples, and we used a selection of 15 Reactome pathways, which we think will play a role in breast cancer. And we added clinical information like age, randomization because patients were treated with two types of drugs, tumor stage, histologically, and so on. And what we found, this type of heat map, let's say, on the bottom here we have sample IDs, and on the right-hand side we have the key outputs from the selected pathway after all the filtering. So we filtered out everything that does not have variation across all patients. And putting together with clinical information, we found that patients having no change in this phosphorylated cTNN complex found in signaling biologic EPase pathway have a longer time to distant metastasis in comparison with patients that have amplification in this complex. When we use somatic mutation data for a cohort of 202 patients, and this overlaps with some of the 344 for which we have copy number variation data. So we got this clustering, like interesting clustering in three clusters. Again, here patients are ID, and here select the key output. And this multivariate survival analysis show that patients with no mutation in this RBL2 complex have longer time to distant metastasis in comparison with the ones that have no change in this complex. However, you can notice we have only 4 patients in this small cohort. They have no change. So we should look for a kind of similar but larger cohort, and indeed we could find in ICGC data set of approximately 550 patients. However, they have different clinical information. I get the clustering, but it's a different survival curve. Okay, so because of this, the biologists from the team started to question if the prediction of this software is accurate. So they came up with two ideas how to test PGMLab output. What happens with the key outputs if for instance, some genes in the RAFMA kinase cascades are regulated, some are downregulated, or what happens with the key outputs of the PIP3 activates AKT signaling when we have also genes upregulated, downregulated, or condition when one is upregulated and some other downregulated. So we started with very simple mock data with patients with 3 states, and we started also with just 4 curated reactome pathways. So I can tell you that the first trial wasn't very easy because we had to manually check each node why the prediction of the PGMLab were not concordant in some cases with the predicted outcomes from biology. So all the outcomes are based on the paper published, experiments. These 2 biologists are pretty sure what they are doing. So we applied PGMLab, then the RAFMA kinase cascade. We have a very good agreement. So we tested several upregulated genes and one which is downregulated. However, the expectation here was to be also for the key output to be in a state of upregulation. For ERBB2, we tested many more conditions, some genes, some upregulated here, the same gene downregulated, but we got a very good accuracy in the end. For cell cycle checkpoints, not so good in comparison with the previous one. However, anything we think after 80% accuracy, it's a good prediction. And for PIP3 activates AKT, this one was the problem with the P10, which was expected to be upregulated, even all the key outputs to be upregulated, even when it's providing inhibitory actions. So in summary, we tested around 522 genes, 326 conditions with the accuracy, overall accuracy close to 90%. And this tables show the true positive versus true negative, false positive and false negative. And we have better results for the first 2 pathways, whereas for PIP3 and cell cycle, it's a bit challenging situation. So because of this, we did another round of testing and developer change a bit the script in order to accommodate the changes. And this was done to improve the export of the reactome results into PGM and also to minimize the manual intervention. Actually, we don't want to do any manual work, so just use the reactome curated pathways. There are around 1,400 of them. Apply PGMLab and get the results. So we can see the accuracy went so much higher, except for signaling for ERBB2 in red here, but 96% is still very good, right? So next, we are testing more pathways like this, but actually want to apply to real data, what we have, and different type of cancers. For now, we are concentrating on pancreatic cancer and breast cancer data that we have. And also, we want to implement PGMLab to accommodate different types of data, only data for the same tumor type. And for the people who don't like or are not comfortable with working with command line command, we are almost ready to release the web version of the tool. And with this, I'd like to thank my PI and to John Bartlett, who provided the breast cancer data, to the PGMLab team. So it's a team of computer science people, biologists, pretty much bioinformaticians, okay, to other people who provided the data, and to OICR for the support. And in the end, if you want to talk more about PGMLab, how it works, it's very easy. to use, friendly. You can email me or call me. And if you know someone in the audience who is looking for a bioinformatician, this is me. Thank you.
Great. We have time for maybe 1 or 2 questions for Cristina.
What is your model based on your machine learning?
So I'm not the one who developed, right? So it's Hossein who is the real developer. So it's based. So this is a probabilistic graphical model. So what I know, it's at the edge of statistics, machine learning, and it's based on graphical theory and machine learning thing. But if you want to know it more, indeed, how it really works, I can give you the information, possible information, who cannot be here in the audience today, unfortunately.
Great. Well, let's thank Cristina again.